Okay, so I want to spend a little time on the term big data, and I'm not too concerned with any sort of technical definition of the term because it probably doesn't exist, but I want to arm you with some of the language that people use when they describe big data so that you can speak intelligently about it when asked. Okay, so the probably the main thing to recognize is this notion of the three V's of big data, which are volume, velocity, and variety. And we talked a little bit about this in a previous segment. So just to repeat, volume is the size of the data, and measured in bytes or number of rows or number of objects or what have you, sort of the vertical dimension of the data. The velocity is, what I'll say here is the latency of data processing relative to the demand for inactivity, and that's maybe a mouthful, but what I mean by that is, how fast is it coming based on how fast it needs to be consumed. And so there's a lot of applications for which interactive response times is increasingly important, if not directly important. Okay, and so when this becomes the bottleneck, when this becomes the challenge, then this velocity term starts to become pretty relevant. And then the one that I think is really pretty interesting to me and is near and dear to my heart with my research is this notion of variety. And so here the problem is, an increasing number of different data sources are being applied for any particular task. And so you need to pull out, ASCII files, as well as download data from the web, as well as pull data out of some database, as well as use some NoSQL system, and so on. And the integration of all these different data sources is a pretty significant problem and can end up occupying a lot of your time. And so I made this point a couple of segments ago about researchers who spend 90% of their time, quote, handling data. This is where a lot of that time is going, this notion of variety. Okay, so all three of these are relevant in performing sort of data science tasks. All right, let me give you another notion, and I'm going to go back to use science examples, and you've seen some of these before. But if you sort of make a plot of number of bytes on the y-axis versus number of data sources, maybe columns of data in a single table, or columns of data across multiple tables, or a number of distinct data sources on the x-axis, you can sort of map out different fields of study or different problems and sort of see where they lie. And so typically astronomy has been challenged by the sheer volume of data, and so they're sort of up here. We're high on the y-axis, but but the number of actual sources in astronomy is not too high. There's telescopes, there's these spectral imagers, and then there's simulations of the galaxy, and so that's relatively few. In, say, the ocean sciences, and certainly in the life sciences, although I only show one example here, the variety is really more of a challenge. The actual sheer scale is not as high as the hundreds of petabytes that can be generated by these telescope infrastructures like the Large Synoptic Survey Telescope. But the number of different types of instruments you can use to acquire data is large and ever growing, right? So you have these glider systems that will go out for months at a time and kind of porpoise through the water. You have autonomous underwater vehicles that are more for short-term missions. There's oceanographic cruises where they deploy these conductivity, temperature, and depth instruments that can take profiles of the water, right? So this is at a fixed XY and a varying Z and a varying T, a varying depth and a varying time, while the gliders are sort of varying in all four dimensions. You have these simulations that are probably one of the largest sources of information. Right, so these can be mesoscale, sort of at the order of the the northern hemisphere or the whole eastern Pacific, or they could be models of a particular bay or inlet or estuary connected to a river and connected to the open ocean, so a much smaller scale thing. So there's a lot of diversity there. And I say stations to mean these sort of fixed stations where there's a particular sensor deployed at one location and just measuring across time. ADCP is a acoustic Doppler something profiler where they're using sound waves to record the time that the sound waves take to bounce off particulate matter in the ocean, and can therefore measure velocity. And so this gives you an entire profile of the velocities in the ocean. You can mount these on the seafloor pointing upwards, or you can mount them on the bottom of a boat pointing downwards, and so on. And then there's satellite images that measure sort of sea color and wave breaking as well. Okay. So fine. So just a little more on the term big data. the notion that Mike Franklin at the University of Berkeley uses, which I like, is that big data is really relative, right? It's any data that is expensive to manage and hard to extract value from. So it's not so much about a particular cutoff. What makes it big? Is it a petabyte scale is big versus a terabyte scale is small, or a gigabyte scale is very small since it fits in memory on your machine? Not necessarily. It depends on what you're trying to do with it, and it depends on what sort of resources and infrastructure you have to bring to bear on the problem. And so in some sense, difficult data is perhaps what big data really means, right? It's not so much about big; it's about being challenging. Okay, and so this is really important to remember, that big is relative. So let me give you a little bit of history of the term big data. There's the earliest notion I could find was from Eric Larson in 1989, where he says, the keepers from Harper's Magazine, that eventually went into a book, the keepers of big data say they do it for consumers' benefit, but data have a way of being used for purposes other than originally intended. So his point was not really about technology at all. It was just a notion that data is being collected for one purpose and being reused for another, which is a theme that I mentioned in the very first segment in this course and we'll come back to over and over again. And so I think he had it right in that sense. So his real point was that, about consumer private data is starting to be commoditized, which was absolutely true and fairly prescient at the time, since it's become a big issue now. But, and especially, perhaps especially impressive that, given that this predates the rise of the internet and it already sort of foreshadows very topical issues in big data, such as ethics and privacy and sensitivity and so forth, that we'll talk a little bit about. But this isn't quite what we mean by big data nowadays, typically, because it didn't have that technology aspect to it. It didn't talk about the challenge of actually managing these data sets. Okay, so another point of reference is that more recent reports from some of these consulting firms get credit for these notion of 3 V's, but really the original source of this was a report from Gartner in 2001, written by a guy named Doug Laney. And so we talked about volume, velocity, and variety, which we've said, but let me just give you a chance to look at these quotes. So in volume, it's he's really talking about sort of business to business. If you think about 2001, this is around the dot-com boom, and so everyone was trying to figure out what this new era of technology was going to get, what the internet was really going to give to them beyond just sort of putting up a web page and serving it out to your customers. How are you going to be able to interact with your supply chain or your vendors and so on? Okay, and so this is what he means by this notion of e-channels. But up to 10x the quantity of data about an individual transaction may be collected. Absolutely true that this data exhaust, this point we've made a couple of times, is giving rise to a larger scale of data being collected. And on velocity, well, it's increased the point of interaction speed, right? So this is that need for interactivity that didn't used to be so required, but as the velocity of all business and all transactions sort of increase, so do the constraints on the infrastructure used to process it. And then on variety, I like this one a lot. So through 2003, 2004, right? So he was being sort of fairly conservative about how far out he wanted to predict. No greater barrier to effective data management will exist than the variety of incompatible data formats, non-aligned data structures, and inconsistent data semantics. And so this is great. This is he could have said this through 2015 and been arguably correct. This problem has not gone away. Okay. All right. So another point in the history of this term big data, there was a series of talks, a lot of work by John Massey, who was formerly the chief scientist at SGI, who would talk about big data being the next wave of infrastress. And so what he meant by infrastress was what's going to really drive the technology forward, where are we going to feel the pain? And his point was that the I/O interfaces was where it was tough. So in particular, disk capacities were growing incredibly fast and still are, and that the latencies are not keeping pace, right? So you can go down to a local store and buy a 3 terabyte drive for probably $200, but the rate at which you can pull data off that is essentially the same as it's been for many, many years. And so now it takes you hours to actually read every byte of data on that disk that you've stored. And so this is a problem because the actual analysis you can do over all this data, we can keep it, and that's fairly cheap, but we can't actually do anything with it because the pipe is so small. Okay, and so this is one of the arguments. He made several sort of very cogent arguments about where the bottlenecks are in the infrastructure, but they all sort of revolved around this idea that large, big data and big data processing were going to be the stress point. And so this is probably a pretty appropriate use of big data, although John Massey has said that he's not sure that he deserves any credit for coining this term, since it's a fairly generic term. and he was using it in one way, and we use it now in a related way, but it's not necessarily that it captures everything we need today, and I probably agree with him. All right, so just another quote about big data sort of today where we're trying to capture exactly how it is being used. You know, the necessity of grappling with big data and the desirability of unlocking the information hidden within it is now a key theme in all the sciences. And, you know, I like this, arguably the key scientific theme of our times. And so we've talked about science, and we talked about the fact that I think what's going on in science is more or less equivalent to what's going on in business. And so I think this is nice, right? It's really maybe the key problem across all fields is unlocking what's going on inside big data, right? Getting some extracting value out of big data. All right. So fine. The final point I want to make is, you know, where does all this big data come from? And we said this a little bit before, but one is data exhaust from customers, right? So we're actually tracking a lot more information about interactions with customers than we used to, right? It's not just about taking their order, it's about monitoring their click stream that they used in order to get to that order. It's about not just about sending advertisements to them, but it's about watching how many clicks are on each advertisement and whether the number of clicks goes up or down depending on where that ad is placed on the web page and so on. Another point that, you know, especially true in science, but I think is also true in business, and I'll give a couple examples of this, is that the availability of new and pervasive sensors, right? We're actually able to get visibility on data sources that we previously couldn't. And I'll give a couple examples of that in a second. And then I think, you know, I mentioned this already, but the technology of data storage, right? Just this capacities of disks has gone up. The cost of per storing a byte has gone down. And so we sort of have this ability to keep everything whether or not we need it, or at least there's a perceived ability to keep everything whether or not we need it. And so people are doing so, right? The other things that they would have otherwise thrown away, they're starting to keep, and then scratching their heads thinking, boy, how might I use this to make predictions and make better business decisions? Okay, so just a couple of examples of sensors that may or may not lead to massive data, but just examples of where we're getting visibility on data sources that we didn't previously have. So one is, you know, the fact that all new cars are going to be equipped with these black boxes that are a lot like what's going on inside airliners have. And, you know, the reason is for forensics in the event of a crash, but they also record a lot of other information. And so insurance companies have similar devices that you can opt in, you can voluntarily plug in to reduce your insurance rates that track your speed, track other kinds of aspects of your driving habits. So this technology, you know, simply would have been hard to imagine, you know, 20, 30 years ago, but now that we have the technology, why not actually start collecting the data from it? Okay. And so while the purpose here is pretty clear, at least for the insurance companies and for these black boxes for crash forensics, you can imagine repurposing that data for other purposes. And in fact, that's what this article was about, was, well, boy, you know, is there a privacy risk here, given that there's one purpose, you know, they're being deployed for crash forensics, but they might be used for other purposes. And for insurance companies, you can imagine how they would collect it with a particular actuarial risk model in mind, but may develop other models in the future, given that now they have this data. Okay, and so I think this is really a theme of big data, is that we're collecting new sources of information, independent of how whether we know how we're gonna use them or not in the future. All right, so let me give you another couple of examples from research here by Shwetak Patel in the Computer Science and Engineering Department, and there are several related devices, and here I just mentioned two of them, HydroSense and ElectroSense. And so both of these devices are intended for consumers to use to monitor their own resource consumption. And so instead of having to kind of rewire your house to monitor the consumption of every device in your house, every faucet and every shower and so on, you can just clamp this device on the main water line coming into your house, and it will monitor the pressure changes associated with every individual device. So it can disambiguate that flow and recognize the signature that every device puts on the pressure changes. And so every time you turn on the shower in the upstairs bathroom or flush the toilet in the downstairs bathroom, this thing can identify when that happens and give you a log of the events. And by analyzing that log, you can tell, you know, which device, where most of your water is going. Is it mostly going for showers? Is it mostly going for dishwasher and so on? ElectroSense is very similar in that every electrical device in your house puts a recognizable load on the signal, on the power signal, that can be read and disambiguated to tell you where your energy is going. Okay, and so these are just examples of new sensors that are coming on the market where data is being derived that otherwise wouldn't have been able to be derived at all.